If you're a programmer, you've almost certainly used compilers, or at least you've heard of them if you've used interpreted languages. So let's break down what a compiler actually is from a really high level perspective. So a compiler basically has 5 main stages, and it goes from lexer to parser to semantic analyzer to some kind of optimizer, and then finally you have the code generation phase, which generates machine code that the machine actually runs. So it's really useful to think of the first 3 phases as you would think of as human speech. So what do you do when you actually hear someone say a sentence? What you do is you first break apart the sentence into words, and that's exactly what the lexer does. So it takes a piece of code and then it breaks them down into tokens, which are basically what words are in human language. And once you have a bunch of words, what you try to do, or what your brain tries to do, is try to construct a sentence out of it. And this sentence is usually some kind of tree structure, and which is what happens when code is translated from tokens to some kind of tree, and it's usually called a parse tree because it's generated by the parser. And then you have a semantic analyzer. And a semantic analyzer too has the equivalent in human speech, which is basically if someone says Jack liked her dog. So you'd first break up into 4 different tokens, and then you'd construct some kind of tree that had the subjects and the objects in the sentence. But then you'd realize that in this case, in the semantic analyzer phase, her is actually referring to Jack, but Jack is probably a guy. So this is this sentence is semantically wrong, and that's what the semantic analyzer does, and it produces errors that you probably see when you compile something that doesn't actually work. And then once you have checked for these things and shown the errors to the user, then you can do some kind of optimization. And optimization, unfortunately, doesn't have an equivalent in human speech, but you can think of some simple optimizations that you might do. Let's say you have some variable x that was set to 0, and then you have a loop that around this variable that basically every time it goes through the variable, all it does is every time it goes through the loop, all it does is set the variable to 0. But then this setting of x to 0 might as well be outside, because let's say this loop goes from 1 to 100. You don't need to do this 100 different times. You just have to do it once outside the loop, since x is not modified by any other part of the loop. And this is something that the compiler does. And when it optimizes, it basically checks that this is the case, and then it takes the x equals 0, puts it outside the loop. And this saves a lot of time, because you don't have to do the same statement 100 times, because there is no consequence of doing that. And once you have done such optimizations, you go to the code generation phase. And the code generation phase is when you translate your high-level language into machine code that your machine architecture processor actually runs. And generally what happens in the code generation phase is that you have to support multiple different machine architectures, like C runs on x86 and ARM chips, and usually what happens is you write one code generation, you have some kind of intermediate language that is translated to multiple different architectures, and usually you don't try to rewrite it, because let's say you have m different languages, and then you have n different architectures that you want to support, and then the number of compilers that you have to write, if you just wrote one big one for each, would be m times n. But then if you translated these m languages into some intermediate language, and then these intermediate languages were translated to n different architectures, then you'd only have to write m plus n pieces, which saves you a lot of time. So this is basically how compilers work. First you break apart into tokens, and then you parse it into some kind of tree, and then you check that there are no semantic mistakes that were made in the tree, and if there were, then you show the errors to the user, and then you do some optimization, and finally you generate code that runs on the machines.